In chapter 26, talking about proportions again, categorical variables. And the good thing is there's only hypothesis tests in this chapter. There are no confidence intervals. So we still know the basic idea, like the basic 4-step process. It's just going to be a little bit different because of what we're doing. Okay? So we're dealing proportions again, but in this case we're dealing with when you have more than 2. If you have 1, we know what to do. We have 1 proportion z-test. If you have 2, we look for the difference. We have a 2 proportion z-test. All right? Then 1. So if we're looking at it, there's a huge diagram I'll give you when we start reviewing. That's like a nice tree that shows you what you should, how you should make your decisions. But today we're going to do Chi Square tests, and there's actually 3 of them. We're going to do 1 today and 2 tomorrow. Okay? So we're going to do goodness of fit today. Then there's 2 other tests, and the 2 other tests are kind of off on their own because the mechanics are identical for their 2 tests, and so it's completely based on the scenario about which test you're trying to do, and you have to be really careful in reading the question to figure it out. In this case, goodness of fit is normally pretty obvious that you're trying to use goodness of fit. All right? The other 2 are too closely related, so it's more complicated. Okay? So chi-square goodness of fit is what the name of the test is. All right, that's what we're looking at today. In the book, they're using an example, so that's what all the stuff up here is. But the example is they're going to sample 256 people and look for their zodiac signs. Now, there's 12 zodiac signs. And so if you were just, any sample of people, you would just assume with a random sample that those people would be equally distributed throughout the zodiac signs. There'd be approximately equal for each different zodiac. All right? Now, that might not be true depending on our sample. Okay? So that's what a goodness of fit test does. It takes a theoretical idea, theoretical distribution, or what we expect to happen, and we compare our observed sample to that. All right? Again, it's from more than 2 proportions. So we're comparing multiple categories. All right? So this is not on your note sheet of the hypotheses. And these aren't in context either. These are just generic. But your null hypothesis is always going to be that your observed distribution or your observed sample matches or is the same as, or the categories are equally likely, something along those lines, as the theoretical distribution or what you expect to happen. All right? So if you think something's equally likely, you can say that. Most of the time it's not equally likely we're looking for. We're just looking for something, our observed sample, to match the expected. Okay? Your alternative then is that they are different. They do not match. They are not the same. Okay? The null is this matches this. Alternative is this does not match this. So with the zodiac signs, we would say our observed distribution of zodiac signs is the same as theoretical distribution of zodiac signs, or easier, since those are supposed to be all distributed evenly, that it's equally likely to get any zodiac sign. And the alternative would be that it's not equally likely. Okay? Everyone go with the hypotheses. So that's step 1 to a test, right? Step 1, hypotheses. The hypotheses for all the chi-square tests will always be in words and they will not be in symbols. All right? So no, you don't have like P equals something or anything like that. You have to put them in the words because there's more than 2 proportions. Okay? There's no easy way to say what you want it to say. All right. Everyone go with that. After you check your hypotheses, you do conditions. And our conditions are a little bit different here. Okay? So your conditions are on the note sheet. The first one isn't something you necessarily have to write out. It has to happen in order for you to do the test. All right, so the first one up here is the counted data condition. In all of these, you're going to get a table of information. So you're going to have some observed sample, and there's like 3 or more categories. Okay? So you're going to have all the information distributed for you. Okay? Now, with that being said, when it says counted data, that means the numbers in the table have to be like integer values. They have to represent like actual people or things. They can't be percentages. Okay, so today we're going to do an activity with M&Ms. It's all about the distribution of colors of M&Ms. So you can have in your sample 10 blue M&Ms, 20 yellow M&Ms, etc., etc. You would not want your data to be in the form of there are 15% blue M&Ms, 30% yellow M&Ms. That's not what you want. So if you get percentages, you need to go back and fix it so that you have your actual values instead. Okay? So if it said you had 100 M&Ms and 20% of them are yellow, then it says in the table 20%, you would need to do 0.2 times 100 and get 20 yellow M&Ms. That's what it means by counts. You have to have actual integer values. We're all go with that. So you don't have to check that. You just have to know that has to happen in your head. Independence. We need all of the counts to be individuals that are independent from each other. This is really easy, though. We're talking about categories when we're doing goodness of fit, right? Zodiac, there's 12 signs. M&Ms, there's 6 colors, all right? Eye color. You're going to fit in a category. So independence, the easiest way to say it is that all of your categories are disjoint, or the same word as mutually exclusive. That means no one that goes in any cell could be in any other cell. Okay? So if you pick out a blue M&M, it can't be blue and green. It's just blue. All right? You have to classify your eye color so it can't be brown and green at the same time. You fit in one category. All right? So the easiest way to say independence is just to talk about your categories being disjoint. So independence still applies. Let's think about your categories. Questions about that? Randomization, still a thing. Still got to check that. So is your sample random, or is it good representation of your population? Still got to check that one. 10%. We don't have to worry about that one so much anymore. Okay? That's not a big of an issue. So independence and randomization. And then there's always some sample size assumption, but this one's a little bit weird and a little bit different. So the sample size assumption here, we have the expected cell frequency. So you're going to have 2 sets of numbers when you do the test. I'll show you an example in a second. You have your observed data, what they give you. Then they're going to tell you how it's supposed to be distributed. All right? We think that it's equally likely, so there should be approximately 22 of each of these things. All right? Or this is 10%, this is 20%, this category is 50%, whatever, whatever. And so we can figure out from our sample size what we would expect to happen. Not what we observed, but what we expect to happen. So not your observed numbers, but your expected numbers all have to be greater than 5. Okay? Now, you have 2 ways to show that. You're actually going to have to do the work anyway, so you could just do the work and then write really quickly all values, expected values are greater than 5. Pretty easy. Or if you do all the work in your calculator and you don't show it, then you need to make sure you say, by calculating all the expected cell frequencies, they're all greater than 5. So you need to mention it. It doesn't take very long. You'll have to do it anyway. Like I said, you have to do it to do the test. So you have to check that regardless. Those are your assumptions and conditions. Any questions about that? So the new one is the expected cell count thing. And we'll see that in a second with an example. So the third step of a hypothesis test is your mechanics. Right? We're doing a chi square goodness of fit test. This is chi square. It's the Greek letter chi, so chi squared. Okay. So chi squared equals. Now, this formula, this big long one, is not like your other test statistics, Z and T. So it has it on the formula sheet for you. It's at the very bottom. It says chi square test statistic equals and gives that formula. There is no guessing involved. Okay, it is there. It looks like a lot, but you're not going to do a lot of it by hand. You can do it with lists in your calculator. Okay, so that'll be helpful. Here's what you do. For each individual category, you take your observed amount minus what you expected in that category and square it. Then you divide by what you expected to happen. And then once you have that number for each category, you add them all together. All right, again, you can do that easily in your calculator. I'll show you how to do it. That's how you calculate the statistic. Okay? Now, chi-square is a family of models. So you have Z models, that's a normal model. T models, there's a T distribution that has a family of T, so you have degrees of freedom to say which model you're using. Chi-square is also a family of models. So chi-square changes, the model changes based on the degrees of freedom. So we have N minus 1 degrees of freedom. Awesome. We're used to that. Except that N is not your sample size. N is the number of categories. All right? So if there are 6 different colors of M&Ms, your degrees of freedom is 5. All right? If we say there's 3 different eye colors you could have, the degrees of freedom is 2. Okay? It's whatever the categories is minus 1. Does that make sense? All right. I'll show you how this math works here in a second. It's not that bad, I promise. Now, once you get chi-square, just like after you get z or after you get t, another hypothesis test, we need to find the p-value, right? How did we find the p-value for z or t? Yeah, normal CDF or t-CDF, right? So chi-square CDF also exists. I would have said the same thing. It's fine. All right, so chi-square CDF also exists in your calculator. So no worries, you can still find p-value. Some things to remember, though. This is a chi-square model. There's one on your notes. They are not symmetric. They're not symmetric at all. They're not supposed to be. That's why you have to check that in your conditions. All right, they're all skewed to the right. Because of that, your chi-square statistic, you're always looking for the upper tail. It's only one direction. Always. Every single time. So in your chi-square CDF in your calculator, it asks for 3 things. It asks for the lower bound, the upper bound, and the degrees of freedom. For chi-square then, your lower bound is always your chi-square number, and the upper bound is always infinity. All right? Because you're always looking for the upper part. Does that make sense? Okay. It's also important to know, because they're so skewed, that your p-values can change really quickly if the degrees of freedom change at all. Okay? So here are 2 chi-square models overlapping each other with the chi-square statistic at the bottom. Let's say we get a chi-square statistic of 10, and we're using degrees of freedom of 5. Small area. Would you agree? Yeah. If you're using degrees of freedom of 9, though, for the same chi-square value, that's a rather large area. That p-value is going to be quite a bit larger. And we only changed the degrees of freedom by 4. With the t distribution, we did t-CDF. They didn't change that much because they were all symmetric. So you changed the degrees of freedom by 4, it didn't change very much. You changed the degrees of freedom by like 100, yeah, it did. But 4 wasn't a big influence. Here, it's huge. Okay, so be careful with that. Make sure you're actually paying attention. Okay. So here's my example I will do, and then we'll do the activity in class. Okay? This is why I think you guys have done this in bio, but I'm not really sure. A geneticist hypothesizes that half of a given population will have brown eyes, and the remaining half will be split evenly between blue and green-eyed people. In a random sample of 60 people from this population, the individuals are distributed as shown in the table, we'll say below, because I moved it. What is the value of the chi-square statistic for the goodness of fit test on these data? So, right now, this is your observed counts. This is from your sample. Okay? This is like we went out and collected data. To do the chi-square statistic, which is what it's asking for, we have to have observed minus expected squared over expected, and we have to add those all together. So I need to come up with the expected amounts. So I would need like an extra section in my table. Now, there's 60 people. So it says that the geneticist hypothesizes that half will have brown eyes. So how many is that? 30. And the remaining half will be split evenly. So what's the other 2 expected counts? 15 and 15. Okay, so you have to do that every time. You're going to have the observed amounts that they give you. You're going to have to find the expected amount. So if we were going to go through and write hypotheses and do the entire test and everything, the null would be that our observed sample data of eye color matches the geneticist's hypothesized distribution of eye color. And the alternative is that it did not. Okay. The conditions You have to be in one of the 3 categories. You can't be in multiple categories, so everyone should be independent. We tell this is a random sample of 60 people, so we have a random sample. And our expected counts, these are the expected counts. Are they all greater than 5? Yes. So we could continue with the chi-square test, goodness of fit. Right? So then we would need to actually do the math. So here's how to do the math in your calculator so you don't have to do everything by hand. This one's only 3 numbers, but I'm going to show you how to do it in the calculator so you don't freak out later when there's more numbers. Go to Stat Edit. You want to put your observed amounts in list 1 and their corresponding expected amounts in list 2. Make sure they match up. Like, do not do them out of order. Don't do brown, green, blue, and then do green, blue, brown. Doesn't make any sense. They got to match up. Then in list 3, we're going to do this part, not the sum, but just this part. So if you go up to the top, to where it says list 3, we can start putting in a function, just like in Excel. You can put in a function that fills it in for you. So we want to do observed, which is list 1, minus expected, which is list 2, squared, all divided by list 2, expected. Does that make sense? All right. Hit enter and it fills in your values for you. Now, the chi-square statistic, though, is the sum of all of those. Again, right now there's 3 numbers and one of them is 0, so I'm sure you could add them on your own accord and it wouldn't be a big deal. But I want to show you what to do in case there's more. Because I don't want to keep going back to, I don't have to write them all down and like add them all together by like retyping them all in. That's silly. So what you would do, this is a new place we normally don't go in the calculator, so I don't know about the Inspire, we'll find it. Go to second stat. It's the list menu. Second stat. Scroll over to math. And number 5 says sum. And use that. Crack me up. I have to get out the table first. So do you guys. Second stat. Math. So make sure you're on like the main screen. Sorry. And then just type in list 3 and it adds all the lists together for you. Kablam, 1.6. Does that make sense? All right, that's your chi-square statistic. It's 1.6. So to answer this question, it just asks you what's the value of the chi-square statistic. Well, it is not less than 1, at least 1, but less than 10. That's where it fits, right? So B is the correct answer. If they ask us to find a p-value, let's say they did, okay? If they ask you to find the p-value, well, then you could go to chi-square CDF. So second distribution menu, it's number 8. The lower would be 1.6. Again, your chi-square is always the lower. Upper is infinity. And in this case, what's our degrees of freedom? 2. Categories minus 1. Then you get 0.449. So then your conclusion would be the same as it always is. Is that high or low? That is high. So we failed to reject the null hypothesis. It seems that the distribution of eye color in our sample matches the distribution that geneticists has hypothesized. Okay, so similar stuff, just different things happening. It's still following that same pattern, though. Questions about that? For now. Then we're going to